So thank you very much, Daniel, for the introduction. So welcome to my session. So I am Kohji Matsumoto of Nagoya University. And today my lecture is the aim of my lecture is an introduction to number theory, and in particular on the prime number theory. That means the study of prime numbers, its behavior, its properties, its distribution, etc. Okay. So I think all of you know the notion the prime numbers, but first I'll begin with the definition of prime numbers. So you see that the positive integer p is called a prime number here if its positive divisor is only 1 and p itself. That means, so if a divides p, then a should be 1 or just the p itself. Okay? And this is the well-known notion, but oh, sorry, this is not necessary. But the most important fact is I will remove my face. So now you can see the full screen mode, all right? Because the most important fact is that any positive integer can be decomposed into the product of prime numbers uniquely. That means, so for example, here there is a 6. 6 can be written as 2 times 3, but it's also equal to 3 times 2. But these are these decompositions, the difference are only the order of 2 numbers, 2 and 3. So you can easily understand that these 2 decompositions are essentially the same. So in this way, we can understand that the composition of prime numbers is unique. So for example, 24 this is 2 to the cubic power times 3, but also written by 2, 2, 3, 2, etc., etc. But all of them are actually essentially the same decomposition. So therefore, we understand that any positive integer can be decomposed into the product of prime numbers in a unique way. Okay. But maybe one remark that number 1 is not a prime, because if we understand that 1 is prime, then we can decompose 6 by 2 times 3 times 1, or times 1, or times 1, etc. So this means so the prime decomposition is, if we include 1 in the set of prime numbers, then the decomposition into prime factors is not unique. You understand? So in this sense, we exclude 1 from the category of prime numbers. Okay. Oh. And now we are talking about how to find the prime numbers. So the method of find prime numbers up to some given numbers is already known in the ancient Greek days, which is discovered by the ancient mathematician Eratosthenes, which is living in this period. And this is also all of you know, I think. But anyway, for example, if you want to count any prime numbers up to the 100, then you first prepare the table of numbers, which is up to 100, and then first exclude 1. 1, this is not a prime. So then the next one, 2, this is prime. So then we found that all multiples of 2, that is multiple of 2, 2, 4, 6, 8, 10, or I mean more, all even integers, that is these one, these one, these one, these one, these are not primes, so we exclude them from the table. Then the smallest remaining number are 3, so we count 3 as the next prime, and then erase all multiple of 3. So 6 is already erased, but 9, 15, 21, 27, etc., etc. Maybe I will continue. So what is next? 45. Which one? This, and this. Oh, it's a fun. 81, 87. What is next? This one, etc. And the next one is 5. Then we erase all multiples of 5 and 7, etc., etc. I think you know, all of you knows. So therefore, now we understand that it is possible to discover all primes up to some given numbers. Of course, we did by hand, but even if the 100 is replaced by very huge numbers, now we are living in the age of computers, so we can count all primes up to some very, very large, huge numbers, such as 1 million, 10 billion, etc., etc. Okay. But then, next we are talking about the first theorem, which is proved among the set of prime numbers. That is the Euclids Theorem. There are infinitely many primes. Euclid is a mathematician, of course, also the mathematician in ancient Greek days. And actually, Euclid is a pronunciation in English way, and exact Greek pronunciation is Euclides. He is living around 3000 before Christ. And this theorem is the first important theorem on prime numbers. And this is quite important because if the number of primes is only finite, then all the properties of prime numbers can be verified just by the finitely many computations. So there is not necessary to build the theory of prime numbers. But Euclid shows that there are infinitely many primes. Therefore, the properties of prime numbers cannot be verified by the finite computation. So it is necessary to develop the theory of prime numbers. So this theorem is, in some sense, this theorem implies that we need the theory of prime numbers. Okay? So now we record the proof of Euclid. This is very famous proof. And it is usually called the proof from the book. So maybe you know the book. What is the book? The book is, no mankind has ever seen this book. This book is in the heaven, and actually in the library of the God. And in this book, all mathematical theorems, I mean all theorems, some of them are known by mankind, but some other theorems are not yet known by mankind, but all theorems the God knows. And in his book, all mathematical theorems are written, and also the all most elegant, beautiful proof of that theorems are also written in this the book. Okay? And all mathematicians agree that this proof of Euclid is coming from the proof, coming from this the book. So this is a quite elegant proof. So we can observe the proof. So maybe you know, but anyway, assume that there are only finitely many primes, P1, P2, after blah, 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 and Pk. And then we consider the number, chapter n, which is a product of P1, P2, blah, 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 Pk, and plus 1. Then obviously n is greater than Pk, so this is not a prime. Therefore, by the prime factorization properties, capital N should be factorized as a product of primes. So therefore, there are only at least one prime number which divides N, which we denote by Q. However, Q should not be one of the P1, P2, Pk, because P1, P2, blah, 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 Pk, any of such Pi do not divide N, because if you want to try to divide N by Pi, then there should be maybe better to write. Oh no. What is this? Oh, what is this? Sorry. What is this? Here. Yeah. So now, because of this, because of this part 1, any P1, P2, Pk cannot divide capital N. So therefore, our prime Q is different from P1, P2, Pk. So we now find new prime Q. So this is a contradiction. So we now prove that there are infinitely many primes. Okay. So this theorem was proved already 2,000 years ago. And so this is the starting point of the theory of prime numbers. But the next stage of the prime number theory was started much later, maybe in the 18th century. So, but before going into the story of discussing the next stage of prime number theory, I will talk about some digression, which is also interested by the ancient Greek people, that is a notion of perfect numbers. So this is another favorite topic of Greek people. So let's sigma n. Sigma n. Sigma n with the sum of divisors of n. That is, sigma n is a summation of d, where d is runs over all positive divisors of n. And positive integer n is so-called the perfect number if sigma n is equal to 2n. Maybe, for example, 6. The divisor of 6 is 1, 2, 3, and 6. So therefore, if we sum up all of these, 6, 1, 2, 3, and 6. If we sum up all of these 4 numbers, this is equal to 11. I'm sorry, 12. So which is twice of 6. So this is agrees with the definition of this one. So 6 is a perfect number. Or maybe better to say, if we sum up 1 plus 2 plus 3, that is all divisors except for the 6 itself, then 1 plus 2 plus 3 is equal to 6. Maybe this is more impressive. Similarly, 28, the divisor of 28 is 1, 2, 4, 7, 14, and 28. But then, if we sum up all of these divisors, except for 28 itself, then this is equal to 28. So therefore, 28 is again the perfect number. Similarly, we know, for example, 496 or 8,128, these are also perfect numbers. And actually, we know that if P is a prime, and 2 to the P minus 1 is also prime, then the product of 2 to the p minus 1 times 2 to the p minus 1. This is a perfect number. This is also proved by Euclid. Maybe we will show the proof. So since 2 to the p minus 1 is a prime, so therefore the divisors of n are, so n is this one. So divisor of n is 1, 2, 2 to the 2, 2 to the square, 2 to the cube, and 2 to the p minus 1, and 2 to the p minus 1 is twice, and 2 to the 2, etc., etc. These are the list of the divisors of n. So therefore, sigma n is a summation of all of those numbers. That is this one. So therefore, this is computed by this 1 plus 2 to the p minus 1 times 1 plus 2 plus 2 to the square plus blah blah blah. So is equal to 2 to the p times 2 to the p minus 1 over 2 minus 1 can be easily calculated to be 2n. So therefore, this n is a perfect number. Okay? But this is proved by Euclid again in the ancient Greek days. But then, more than 2,000 years later, Leonhard Euler is, I think you know that he's the greatest mathematician in the 18th century, born in Switzerland and working in Russia and Germany, etc. And he wrote many theorems in his life. And this is one of his theorems. So if n is an even perfect number, so then all even perfect number is of the form which is indicated by Euclid. Okay? That is, even perfect number should be of the form n is 2 to the k minus 1 times 2 to the k minus 1, and 2 to the k minus 1 is a prime number. And if this 2 to the k minus 1 is prime, then k itself is automatically prime. Because it's easy, because if k is, so this, if k is not a prime, k should be the product of a times b, but then 2 to the n minus 1 divide 2 to the k minus 1, which is impossible because now we assume 2 to the k minus 1 is prime. So therefore, k is automatically prime. So therefore, if 2 to the k minus 1 is a prime, then k is also prime. So this is exactly the form which is indicated in Euclid theorem. Okay? So now, proof. So let n be an even perfect number. Then n is even. So therefore, we can write n is 2 to the k minus 1 times b, and k is greater than 1, and b is odd. Okay? And on the other hand, because n is a perfect number, therefore, then by the definition, sigma of n is equal to 2n. That is, sigma of 2 to the k minus 1 times b is equal to 2 to the k times b. Okay? So now, next, it is easy to show this property. So the function sigma has a following property that if L and M is coprime, then sigma of Lm is equal to sigma L times sigma M. This is not difficult to prove, but anyway, this is included in the exercise associated with this lecture. So maybe if you are interested, you will go to the exercise room in this Friday and solve this problem. So here I will assume this one. Then this left-hand side of this one is divided into this one. But this sigma of 2 to the k minus 1 is easy to compute. That this is just 1 plus 2 plus 2 to the 2 plus 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 etc., which is easily computed by 2 to the k minus 1. So therefore, from this formula, we now obtain the sigma b is equal to the 2 to the k times b over 2 to the k minus 1, which is equal to b plus b over 2 to the k minus 1. Can you follow me? So now, sigma b, this is of course integer. And b, this is also integer. So therefore, the remaining part here, this is also integer. Okay, that means b can be divided by 2 to the k minus 1. And therefore, this is an integer, and moreover, this is a divisor of b. This implies the sigma b is actually, we define sigma b is a sum of all positive divisors of b. But now, on the right side, there are only two parts, two divisors of b. That means b has only two positive divisors. So just only two positive divisors should be 1 and b itself. B itself and 1. But this is already b. So therefore, the other divisor, this one, b over 2 to the k minus 1, should be equal to 1. Okay? Oh. So now we can conclude the proof that now b has only two divisors, which means b is a prime. And moreover, we know that b over 2 to the k minus 1 is exactly equal to 1. That is, b is equal to 2 to the k minus 1. So therefore, our n is, we put n is this. N is 2 to the k times b, which is here. N is 2 to the k minus 1 times b, but b is 2 to the k minus 1. So n is now, we find this one. So this is a form which Euclid indicated. So now we complete the proof of Euclid's theorem. That is the all even perfect numbers should be of the form n is equal to 2 to the k minus 1 times 2 to the k minus 1. Okay? Okay. So now Euler's theorem, we know everything about even perfect number. But then how is the odd perfect numbers? Odd. So actually here we know very little things. So far no odd perfect numbers are known. And the mathematicians believe that there are no odd perfect numbers, but no one has succeeded in proving it. So now here you can find one open problem, unsolved problems in number theory. This problem is, in some sense, this problem was raised in ancient Greek days, but still no one can prove it. Now it is known that, for example, n is an odd perfect number, then n is greater than 1, 10 up to 10 to the 1,500, and n has at least 10 distinct prime divisors, etc., etc. So this fact implies that odd perfect number looks quite impossible. But still, no one can prove this fact completely. So maybe if you are interested enough, please try to prove this odd perfect number problems. Yeah. Okay. So now we are going to the going back to the street of the discussion of prime numbers, and we are now talking about the zeta function. So zeta function is introduced by Euler. Euler is a person who proved the theorem of the even integer, even perfect numbers. But Euler is also regarded as a father of analytic number theory because he first introduced some analytic tool to study the theorems in number theory. So to explain Euler's invention, we need the notion of infinite series. So maybe are you familiar with infinite series? So for example, 0.33333. This is 3 over 10 plus 3 over 100 plus 3 over 1000 plus etc. etc. And the right hand side approximates a certain number, which is we call it at 1/3. Okay. Similarly, if the absolute value of x is less than 1, then we know this infinite series 1 plus x squared plus x cubed plus and so on is equal to the, or maybe is converges to the 1 over 1 minus x. These are the notion of infinite series. And by such an infinite series, we can define many functions. And among them, there is a so-called zeta function, which was introduced by Euler. That's written as the following infinite series. So zeta s is defined by this infinite series, 1 plus 1 over 2 to the s plus 1 over 3 to the s plus, etc. Okay? And s is to be regarded as a variable. And this series is, when s equals 1, this series goes to infinity. This can be proved easily, so like this. So when s equals 1, the series is this one, 1 plus 1/2 plus 1/3 plus and so on. And we consider the first two terms. And next this, sorry. Next to these two, I cannot write. What happened? Oh, what? Oh, coming back. Okay. So these 1/3 and 1/4, we group this 1/3 and 1/4. And the next four terms, 1/5, 1/6, 1/7, 1/8, we group this one. And then in this group, we replace 1/3 by 1/4. And in this group, we replace 1/5, 1/6, 1/7 by all of them by 1/8. Then obviously, the right-hand side is smaller. But however, this right-hand side is 1 plus 1/2 plus, and these groups equal to 1/2, and these groups also equal to 1/2, and 1/2, 1/2, 1/2. So this is equal to 1 plus 1/2 plus 1/2 plus 1/2 plus, etc. So infinity meaning 1/2. So this is obviously plus infinity. So the original series is, of course, larger than this series. So therefore, this original series should tend to infinity. This means when s equals 1, our zeta function is divergent. But however, when s is greater than 1, it is possible to show that this zeta function tends to a certain positive number, such as, for example, zeta of 2. It is known that zeta of 2 is equal to pi squared times 6, and zeta 4 is equal to pi to the 4th power over 90, etc. And it is known that pi to the k, pi square, pi cube, all such pi, the power of pi are irrational numbers. It is known. So therefore, zeta 2, zeta 4, zeta 6, all values of zeta function at even integer points are irrational numbers. And indeed, maybe I will remark that actually pi is a so-called transcendental number. That is, pi is not the root of any algebraic equation of any degree with rational coefficients. That is, so therefore, zeta of 2, zeta of 4, zeta of 6, all of them are also transcendental numbers. Okay? So now we are talking about the even integer points, but how about the values of the zeta function or odd numbers, odd integers? Actually, this is another big difficult problem, and no simple expression is known. I mean that, of course, by computer, it is possible to compute the values of the zeta function at all the integer points at, for any decimals, but such expression, simple expression, in the even integer case, there is such a simple expression. No, but no such simple expression is known for all integer points. We only know the following several facts. For example, zeta 3 is an irrational number, which is proved by the French mathematician Alperi in 1978. And then another French mathematician River proves there are infinitely many odd integer points which are irrational points, irrational numbers. And furthermore, at least one of zeta 5, zeta 7, zeta 9, and 11, each one of them are irrational. This is proved at Zudrin 20 years ago. So you can see that these are the result of not so old results, only 20 or 30 years ago. So and it is widely believed among mathematicians that all values of the zeta function at all the integer points are transcendental. But again, this cannot be proved by anyone. So this is another open problem in number theory. Okay. Yeah. Okay. So let's go to the next section. Now we will discuss the connection between this zeta function and the prime numbers, which is connected by this Euler product. Okay. So Euler product is as follows. So zeta function is given by this infinite series expression, or maybe by using the summation symbol like this. But the zeta function has a following another expression, which is given by infinite product 1 over 1 minus 1 over 2 to the s to the minus 1, 1 minus 1 over 3 to the s to the minus 1, etc., etc. And these 2, 3, these denominators ones over all prime numbers. That is the product of the quantity of the form 1 minus 1 to the p to the s to the minus 1, and product among all primes. Okay. This is called the Euler product. Oh, this is called Euler product. And so we now show two expressions, the infinite series expression and the infinite product expression of the zeta function. So now it is necessary to show these two expressions are equal. Okay. For this purpose, we recall the following well-known infinite series expression, and we put x is equal to p to the 1 minus 1 over p to the s. This is x. Okay. So then 1 minus 1 over p to the s to the minus 1 is expanded to 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the qs, etc., etc. So therefore, the first two terms, this one is our product expression, and the first two terms are 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s, and we insert this expression into these terms and expand everything. So what happens? Then the first part is this one. The second part is this one. So the denominator is 2, 4, 8, that is the power of 2. And here the denominator is 3, 9, 27, the power of 3. And expand everything. Then 1 plus 2 to the s, 3 to the s, 4 to the s, 6. 6 is from the 2 times 3, and 8 to the s, 9 to the s, and 12. 12 is coming from 6, 4 times 3, etc. So now you can see that here in the denominator, all numbers consisting only of 2 and 3 appear. Okay? Okay. So next, we take the next factor 1 minus 1 over 5 to the s into consideration. Then, by expanding similarly in the previous page, we now find the expansion in which the denominator includes all numbers, which is consisting of 2, 3, and 5. Okay? Therefore, now we consider the product of first k primes. Then, by expanding, we obtain the infinite series expression in which in the denominator all numbers which are consisting of p1, p2, blah blah blah, pk, first k primes. All numbers consisting of only the first k prime factors are appearing in the right hand side. Okay? And actually, all positive integers can be written as a product of primes. So therefore, any positive integer n appears, any positive integer n appears on the right-hand side if we take k sufficiently large. So therefore, finally, if we take all prime numbers, then all positive integers appear in the right-hand side. And this is a infinite product expression, and this is the infinite series expression of the zeta function. So the two expressions are now, we proved they are the same expressions. So we are done. Okay. So now we prove this identity here. Okay. From this identity, we can observe the following interesting consequence. That is, the left-hand side is when s tends to 1, the left-hand side is, as we saw already, when s equals 1, this left-hand side tends to infinity. So therefore, when s tends to 1, the right-hand side also tends to infinity. But right-hand side is actually, when s equals 1, this tends to the product of 1 minus 1 over p to the minus 1. So therefore, if there are only finitely many primes, then this is the product of only finite factors. So this should be some finite number. But this is contradicts with the fact that this is the left-hand side is infinite. Okay, so therefore this should not be the finite number. So this implies there should be infinitely many prime numbers. So this is an alternative proof of Euclids theorem that there are infinitely many prime numbers. So this is also noticed by Euler, but this proof is quite important because this is the first occasion in the history of prime number theory that is some analytic fact, some infinite series behavior is used in the study of properties of numbers. So this is the beginning of the analytic number theory. Okay. Well, okay. Let's go further. Actually, by studying more closely, it is possible to show that only Euler's argument is only shows that there are infinitely many primes, but actually we can show that this infinite series, the reciprocals of prime numbers p, this tends to infinity. So maybe, for example, we already show that all reciprocals of all positive integers are going to infinity, but all reciprocals of square numbers is actually, this is actually equal to zeta 2. So therefore, this is, I already mentioned, this is actually finite number, which is pi square over 6. So therefore, some infinite series is going to infinity, and some infinite series is going to some finite number. But now, this infinite series consisting of the reciprocals of primes tends to infinity. So in this sense, the set of all prime is larger than the set of all squares. Do you understand the meaning? So we will prove this. So we call the Euler product expansion, and now take the logarithm. Then, so we will go to this way. So we will take the logarithm. Then this is the left-hand side, and this is the right-hand side. But the right-hand side, we change the order of log and product. Then product is turned into the summation, and this expression. And then we consider the situation when s tends to 1. So then, repeatedly, we use that this left-hand side is when s tends to 1, this inside the log symbol is tends to infinity. So therefore, this itself should be infinity. And on the right-hand side, here we use the notion of Taylor expansion of the logarithmic function. Maybe some of you are not familiar with Taylor expansion, but please accept. So it is known that the minus of log of 1 minus x can be expanded by x plus x squared over 2 plus x cubed over 3 plus, etc. So by using this expansion and inserting this expansion to the right-hand side, we now know that the right-hand side is equal to this expression. Okay, and then we take up this first part, which is the summation of p of 1 over p to the s and the remaining part. Okay. Now we find that this remaining part qs consists of this p to the square, p to the cubic power, p to the fourth power, etc. And this and this, these two are estimated by this 2 over 2 to the p to the 2s. That is, this here, p to the 3s is smaller than p to the 2s. So therefore, we replace this p to the 3s by p to the 2s and replace here. And this numerator 2 is coming from the fact that there are two terms. Okay? And similarly, these two terms can be estimated by this one, etc., etc. And then this is equal to summation of p to the 2s, 1 over p to 2s plus 1 over p to 3s plus etc. But obviously, this is less than this. If it is the summation of 1 over n to the 2s, where n runs over r positive integers. But then, when s tends to infinity, when s tends to 1, this tends to summation of n to the square. So this is pi square over 6, the finite number. So therefore, qs is when s tends to infinity. S tends to 1. Qs remains finite. Okay. So what happens? So we are talking about this one. So the right-hand side is this summation of p plus qs, but now we know qs remains finite when s tends to 1. Therefore, the remaining part, this is the remaining part. This is the remaining part. This should tend to infinity when s tends to 1. That is, this infinite sum of the reciprocals of p should tend to infinity. Okay. So this is the proof of the theorem. Okay. So now we can understand that by using the properties of the zeta function, we can show some deep properties of prime numbers. And actually, studying the zeta function more closely, we can obtain some deeper and deeper results in the distribution of prime numbers. And the landmark of the prime number theory is so-called the prime number theorem. Prime number theorem, that is the pi x. This denotes the number of primes up to x. For example, pi x is, for example, pi to the 10, less than 10, there are 4 primes, 2, 3, and 5, and 7. So pi 10 is 4. Pi 100 is, maybe some of you know that less than 100, there are 25 primes, etc. So this is the counting function of prime numbers. And the prime number theorem says that this pi x can be well approximated by the function, the simple function x over log x. The rigorous meaning of this terminology is well approximated. I will mention later. But anyway, this is a prime number theorem. And this is conjectured by the Legendre and Gauss around the beginning of the 19th century. And almost 1 century later, established by the Mahan and Valle-Poisson independently in 1896, which is a rather the end part of the 19th century. Okay. So, however, to prove the prime number theorem, it is necessary to consider the zeta function as a complex function. Zeta s, we define zeta s when s is a real variable, but hereafter we regard s as a complex variable. That s is we write s is sigma plus it, and sigma is the real part, and t is the imaginary part, and r is the square root of -1. Okay. Then we know that, so this is a real, so maybe here, oh, sorry. So here is a s equal 1, and the zeta function is defined when s is greater than 1. Or now in the complex situation, we can define the zeta function by the infinite series when the real part of s is greater than 1. And here there is a s equal 1, and we know that at s equal 1, zeta s is divergent. However, in the complex function theory, there is a technique of so-called analytic continuation, and by using the method of analytic continuation, we can extend the definition of the zeta function into the plane where the real part of s is less than or equal to 1. And of course, today I don't want to mention the details of how is the theory of analytic continuation, but it is possible. And by using this technique, we know that the s equal 1, the point s equal 1 is the only point where the zeta function is not finite. This is called the singular point. And for any other s, any other complex s, which is not equal to 1, we can define by the method of analytic continuation the value of zeta s as a certain finite complex number. This is quite an essential point of the theory of zeta functions, and this was done by German mathematician Bernhard Reumann in the middle of the 19th century. Okay. Well, so now we proved this theorem. In the plane, here is 1, and in this plane is the plane where the original definition of the zeta function is valid here. And in this half plane, that is, the real part is greater than 1, we can show that zeta s is not equal to 0. This is actually easy because now we consider the reciprocals of the zeta function, which is this product, but without the -1 factor. Okay, so it's this one, and we expand this right-hand side. Then you can find in the denominators, if we expand this right-hand side, in the denominators, only the numbers of the form p1, p2, pk to the s, here p1, pk our distinct prime numbers. Such numbers are only appeared in the denominators. So denominators is like this: P1, P2, Pk to the S. And for each time there is a signature -1. So in the numerator there is -1 to the K. Okay. So therefore, we now define the following function mu n, which is given by the -1 to the K when n is a product of K distinct primes and mu n is 0 otherwise. Then we can write the reciprocal of the zeta function is equal to the infinite series. Here, the numerator there is a this function, Möbius function, and the denominator is n to the s. By the definition of this Möbius function, it is true obvious that the absolute value of the Möbius function is less than 1. So therefore, the absolute value of the reciprocal of the zeta function is this one, and less than this one. And here is an absolute value of Möbius function, but it's less than 1. So which is this one. So this is obviously zeta of sigma, which is finite when sigma is larger than 1. So the reciprocals are finite, which means zeta s does not equal to 0 when sigma is larger than 1. So this is a proof. Okay. So now we know that when real part s is larger than 1, then zeta function has no zeros, which we call the zero Fourier region of the zeta function. But actually, we can show the following theorem, which is due to Tahtamar and Dora-Vare-Poussin. That is, this zero Fourier region is, maybe we can write again the figure. Here is a 1. So we prove the zero Fourier region here, which is larger than the real part is larger than 1. But this theorem shows that this line, the real part is equal to 1, is also a zero Fourier version. Okay? And I don't want to show the proof of this fact here, but this is a key fact in the proof of the prime number theorem. Okay? So maybe I will mention here how is the distribution of zeros of the zeta function in other areas. That is, when real part of s is less than 1. And actually, there is a following theorem. In the half plane, this is 0, and in the half plane, the real part of s is less than 0. The only zeros of the zeta function is here, -2, -4, -6. That is the even negative integer points, -2, -4, -6. These are zeros of the zeta function in this plane, and those are only zeros of the zeta function. This is called the trivial zeros. Of the zeta function. So therefore, we now find how is the distribution of zeros of the zeta function in this half plane and in this half plane. So the remaining part is only here. That is a strip where the real part is in between 0 and 1. Okay? And the zeros of the zeta function in this region are called the non-trivial zeros. But it is now known that it is extremely difficult to determine the behavior of those zeros in this region. But Riemann already noticed in his famous paper published in 1859 that it is probable that all the non-trivial zeros in this strip are on the line. Real part of S is one half here. That is the central line of this strip. So this is a very, very famous Riemann hypothesis, which is still unproved open problem in number theory. And many people believe that this is the most important unsolved problems in the whole of mathematics. Okay. So this is a very, very big unsolved problems. And because of this great achievement, so we now call that zeta function is usually now called the Riemann zeta function. Okay. Okay, so now we are talking about how to prove the prime number theorem. So we first give the rigorous definition statement of the prime number theorem. It's this one: pi x is asymptotically equal to x over log x. Here, this symbol, the meaning of this symbol is the fx is asymptotically equal to gx if the quotient of fx over gx is, when x tends to infinity, it goes to 1. That is, in our case, the quotient of pi x and x over log x, the quotient of these two quantities tends to 1 when x tends to infinity. This is the meaning of the asymptotically equal symbol. Okay. And now we maybe first I will mention the meaning, the round-up symbols. Round-up O symbol and round-up small o symbol. So this is a symbol. If fx is large O of gx, big O of gx, if there exists a positive constant c such that the absolute of fx is less than c times gx. And also, we write fx is small o of gx when the quotient of fx over gx tends to 0 when x tends to infinity. These two symbols are called the Landau's big O and small o symbol. And if we use this Landau's small o symbol, we can write the prime number theorem like this: pi x is x over log x plus small o of x over log x, or maybe 1 plus small o 1 times x over log x. So this is a convenient expression. So later we will use this notation. But anyway, so this is a prime number theorem. So this is our final target of this lecture. Okay, so towards the prime number theorem, the first meaningful contribution was done by the Austrian mathematician P.L. Chebyshev at around the 1850, the middle of the 19th century. He proved the following two facts. First, pi x is in between c1 times x over log x and c2 times x over log x. And I don't write down the explicit value of c1 and c2, but actually Chebyshev obtained c1 is something like 0.9, etc. And c2 is something like 1.1, etc. So rather close to 1. And moreover, if the limit, this limit exists, Chebyshev showed that this limit should be equal to 1. He couldn't prove the existence of this limit, but anyway, you can see that these two results of Chebyshev are quite close to the final statement of the prime number theorem. Okay. And more important point is, in the course of his study, Chebyshev introduced the following two functions to some auxiliary functions, theta x and psi x, which is now called the Chebyshev functions. So the definition is like this. Theta x is summation of log p, where p is a range of all prime numbers up to x. And psi x is the summation of lambda n. But lambda is the so-called von Manglet function defined as follows. So lambda n here, lambda n is takes the value log p if n is a prime power p to the r. Only when n is a prime power, then lambda n takes the value log p, and all other situations lambda n is equal to 0. And the second Chebyshev function is that denotes the psi x is given by the summation of lambda n, where n runs over all positive integers up to x. So this is called the von Manglet function. And so these two functions are closely connected because psi x is so the summation lambda n, but lambda n only has a value when n is a prime power. So therefore, it is the summation log p, for which the summation is runs over all prime power p to the r of less than x, which is when r equal 1, then this is just a prime numbers. So when r equal 1, this implies this one, which is exactly equal to theta x, and some remaining part. So by this relation, these two Chebyshev functions, psi x and theta x, is closely connected. Only the difference is here. Okay? Can you follow me? Okay, so let's go to the next proposition. So now we are talking about the following result. So theta x is x plus small o x. If this is valid, then this is valid. This is the prime number theorem. That is, if we show that if we show theta x is asymptotic, if theta x is asymptotically equal to x, then pi x is asymptotically equal to x over log x. Okay? So therefore, now the prime number theorem is reduced to this expression. So I will just sketch the proof, how to prove this proposition. So theta x is, this is the definition of theta x, and log p, all of log p is less than log x. So we replace log p by log x, and which is can be taken out from the summation symbol. So log x times the number of prime numbers up to x, which is just equal to pi x. So therefore, by this computation, we know that theta x over log x is less than pi x. On the other hand, in the opposite direction, we can show that theta x is actually less than rather than this one. Here we restrict summation from x to the 1 minus epsilon to flow to x. So therefore, this is the summation in the smaller range. So this is obviously less than theta x. But then log p is larger than log of x to the 1 minus epsilon. So we can take out this one. And then therefore we now know that this is equal to 1 minus epsilon times log x times pi x minus pi of x to the 1 minus epsilon. But this is obviously smaller than pi x. Therefore, this part is written by pi x times 1 plus small o 1. So therefore, totally speaking, this implies theta x over log x is larger than 1 minus epsilon times pi x times 1 plus small order 1. So therefore, combining this inequality and the previous inequality of the opposite direction, we now know this two-sided inequalities, and epsilon can be taken arbitrarily small and small and small, and then epsilon, if we take epsilon small and small and small, then this is goes to 1. So therefore, finally, we can find theta x over log x is theta x over log x. Oh no. Theta x over, oh no. Log x, log x is, is, I'm not familiar with this go to webinar systems, so sometimes, oh yeah, now it's coming, pi x, okay? So therefore, this obtains. So this is the proof. Okay. So the next, another proposition. We are now talking about the following proposition. That is, if psi x is asymptotically equal to x, then theta x is asymptotically equal to x. This is the contents of this proposition. And in the previous proposition, we already shown that if this is true, then pi x is asymptotically equal to x over log x. So therefore, now we can say that prime number solver is reduced to this expression. So to prove this proposition, it is enough to record this relation. Psi x and theta x is the difference of psi x of theta x is just this sum. Here, the power r is not less than 2. So therefore, we divide. This is p to the square. This is p to the cube, and etc., etc. So therefore, this part is written by like this, like this. And if x to the 1 over k is less than 2, then the prime, which is less than x to the 1 over k, does not exist because the smallest prime is p. Smallest prime p is 2. So if this is less than 2, there is no such prime. So therefore, this x to the 1 over k will stop when k is k satisfies this one. So therefore, k should be, this k should be the largest integer for which x to the 1 over k is larger than 2, which implies 1 over k times log x is larger than log 2, which implies k is less than log x over log 2. Okay? So therefore, what happens? Therefore, therefore, the above is, so log x times this one. So maybe I will This is maybe a bit okay. So this sum is all log p is less than log x. So we replace these log p by log x and take out from the summation. Then we obtain this expression, and these summations are less than x to the 1 over 2, x to the 1 over 3, and blah blah blah, and x less than 1 over k. So therefore, this is log x times k times x to the half, and finally this is this one, which is obviously small r of x. So therefore, this part, this is a difference of theta x and psi x, which is less than ox, which implies theta x is psi x plus small r of x. Therefore, if psi x is x plus small r of x, then theta x is also. This is a proof of this proposition. So now we obtain that the prime number theorem, the proof of the prime number theorem is reduced to the proof of this asymptotically equal psi x is equal to asymptotically equal to x. And then from this point, we can connect this argument with the theory of the Riemann zeta function. Yeah. So now we are talking about the Riemann zeta function again. But from now on, I will use some fact of calculus. That is calculus, I mean differential calculus and the integral calculus. So maybe some of you are not familiar with that calculus, but now our argument is almost over. So please listen to maybe more than 10 minutes or something like. Okay, so now we recall the Euler product expression of the zeta function. Take a logarithm. We found the log of zeta s is written by this infinity series, where the summation is round over r prime. And now we differentiate the both sides. Then the left-hand side is zeta prime over zeta. And zeta prime means derivatives of the Riemann zeta function. And the right-hand side is by considering the differentiation of the logarithm. We obtain this one. And in the denominator, we again use the expression 1 over 1 minus s is 1 plus x plus etc. We use this expansion to this denominator part to obtain this one. So this is the expression. But now you can see that here, this is can be written as a summation of this infinite series, where the numerator is the von Manglet function lambda n. Okay. So now this is a very fundamental expression. The left-hand side is a Riemann zeta function, some quantities related with the Riemann zeta function, and the right-hand side lambda n. This is connected with the prime numbers. So this is a bridge in between the theory of the Riemann zeta function and the theory of prime numbers. This is very important key formula. And by using this formula, we now use the theory of complex integration. So now we define the following integral I, which is this one. So this is a complex integration. So here maybe there is a C, and we write this is a complex plane C minus I infinity to C plus I infinity. We are considering the following path of the integration. That means, or maybe if you are not familiar with the complex integration, maybe you can understand that when S is on this line, S can be written as C plus IT. So therefore, if we insert this expression of C plus IT in this form, you can find this is just some usual integration on the real line, but includes some I equals square root of -1. Okay. Now, so maybe this. We already know this expression that zeta prime over zeta is expressed by the infinite series involving the von Mangold function. So to insert this expression into here, then we obtain this expression that is I is written by this infinite series and changing the order of integration and summation, we obtain this expression. The summation of here is a lambda n, and inside there is some complex integration of this form. So we compute this form. Then so our problem is to compute this type of complex integration. So now you see this is the integral from C. This is C minus I infinity to C plus I infinity. But then here is a y. So y is some positive number. But if y is in between 0 and 1, so then this y to the s is when s is a complex number, but when the real part of this y to the s, the absolute value of y to the s is y to the real part of s. So if real part of s is going to plus infinity, when sigma tends to plus infinity, if y is between 0 and 1, this y to the sigma goes to 0. So therefore, this integrand goes to 0. So therefore, if we move this path of integration to the left, right, and right, then this integral goes to 0. So therefore, simply, when y equal in between 0 and 1, jy is simply equal to 0. However, if y equal rather than 1, this y to the s, the absolute value of y to the s, y to sigma is tends to 0 only when sigma tends to minus infinity. So in this case, we should move this path of integration into the left side. Then again, this integral tends to 0. But however, in this case, in the process of moving this integration, we encounter the point s equals 0. But s equals 0, this integrand has a singularity. So the situation is a bit different. This is the place where the so-called residue character is important. And actually, we know we can show.
Excuse me, Professor Matsumoto. We don't hear you anymore. I think your microphone may be hidden by something.
Oh, oh.
Yes, it seems to be much better now. Thank you.
Much better? Okay, sorry. No. Now it's okay? Hello?
Yes, thank you.
Okay. So, but now, so now, so because of the point s equals 0 is encountered, we should calculate by the residue calculus. Maybe you don't know, but here is a point where residue calculus comes into play, and the residue at s equals 0 should be computed by computing following limit. So this is the integrand, and multiply by s, and take the limit s tends to 0, then the result is 1. So therefore, in this case, we know jy is 1. Therefore, as a conclusion, we now obtain this expression. This one. So our integral is simply when n is less than x, it's 1, and n is larger than x, it's 0. So therefore, our integration, our quantity is simply this one. Only when n is less than x, this integral is equal to 1, so lambda n remains. So this is exactly psi x. So we now know that I is just equal to psi x. So our aim is psi x is asymptotically equal to x. This is our aim. We already know that if we prove this one, we can obtain the prime number theorem. So now we know this is equal to I. So now our final aim is to show this integral I is asymptotically equal to x. But now, finally, we can see this is our final aim. This one, okay? Now again, we use the residue calculus. So the relevant singularities are coming here. S equals 0, then this is this tends to infinity because of the existence of this factor. And s equals 1, this is a singularity of the zeta function itself. And one more, here zeta s, here is a zeta s in the denominator. So therefore, if there is a zeros of zeta s, we are now find the singularity of this integrand. But we already know that zeta s is not equal to 0 when sigma is larger than or equal to 1 by the theorem at Adamah and Rabare-Poussin. So therefore, now we move the path of integration into the real part s equal to 1 without encountering the zeros of the Riemann zeta function. Actually, even a bit more. So what happens? So we, oh no. So we now obtain the following way. So, yeah. So there is the original path, but here is 1, but here is 1. But we move the path from here to a bit left of the line 1. There is no zeros of the zeta function, so the only singular point is s equal 1, and this singular point s equal 1 gives a residue, which is this one here. This so I should be the residues coming from the point s equal 1 and the remaining integral. But s equal 1, here the integral, the residue is, because we know the zeta s is a singular point of at s equal 1, which means zeta s is asymptotically equal to 1 over s minus 1. Then differentiating, we obtain zeta prime is asymptotically equal to 1 over s minus 1 to the square. So by using these data, we obtain the zeta prime over zeta is asymptotically equal to 1 over s minus 1. So therefore, the residue of this quantity is equal to this one, and this one, this one, this one, and finally equal to x. So therefore, this is this part is x. So this formula implies I is x plus remaining integral here. But it is possible to show that this remaining integral is small o of x. So therefore, now we conclude I is asymptotically equal to x. Okay? So now the proof of the prime number theorem is completed by just a very roughly sketch. But anyway, this is a story of the proof of the prime number theorem. Oh. Maybe it is better to say my final comments. That is, so now we maybe we recall that C is here and 1 is here, and we know that this zeta function is 0 free here, so we move the path of integration just like here and prove the prime number theorem. But as we already mentioned, that by the Riemann hypothesis, which is of course not proved yet, but if Riemann hypothesis is true, then all the trivial, all the zeros of the Riemann zeta functions are on this line, which means up to 1/2, these are zero free regions of the Riemann zeta function. Therefore, we can move the path of integration to this part. Maybe this is 1/2 plus epsilon for any positive epsilon. Okay. So if we can move the path of integration here without encountering the zeros of the zeta function, then we can discuss similarly as above, and finally we obtain the following result that is much better than the present form of the prime number theorem. That is, x is equal to x plus O of x to the 1/2 plus epsilon. So the our error term is just x plus small o x. But if we assume the Riemann hypothesis, we can improve the error estimate to O of x to the 1/2 plus epsilon much better. And moreover, it is known that this exponent 1/2, under the assumption of the Riemann hypothesis, it is known that this exponent 1/2 is the best possible, which cannot be replaced by a smaller constant. That means the Riemann hypothesis, if we assume the Riemann hypothesis, we can obtain the best possible error estimate in the prime number theorem. So we know the much better estimate in the prime number theorem. Okay, so this is this is one of the reasons why the Riemann hypothesis is quite important in number theory. But of course, there are many other reasons why the Riemann hypothesis is important. I cannot exhaust all of those materials, but anyway, this is one of the reasons why Riemann hypothesis is so attracted by many mathematicians. Okay, so my talk is over. Thank you very much. First, so odd perfect number. So we know nothing, okay? And even perfect number. So even perfect number is, so now we know that Euler's theorem that if this is a form of the even perfect number, so the problem is reduced to the to find the primes for which 2 to the k minus 1 is a prime. Okay, so as I said, 2 to the k minus 1 is a prime, then k is also prime. So it is written by here. So the problem is to find a prime p for which 2p to the minus 1 is also prime. Okay? So such prime is called the Mersenne primes. So the problem is reduced. So to find the perfect number is reduced to the problem that to find Mersenne primes. And there are some criterion, how is criterion whether n is a Mersenne primes or not. But still, it is difficult to find Mersenne. Now we know many huge Mersenne primes. You can find the web page on Wikipedia or something like that. You can find so large Mersenne numbers. And now no, but still we know only finite many numbers of Mersenne primes, and no one can show that is there infinitely many Mersenne primes or not. This is still also an open problem in number theory. Maybe you can try. You can attack. Okay. This is but this is just some intuitive. This is I said that to compare these two series. So in some sense, this is divergent and this is convergent. So in that sense, the set of all primes is larger than set of all square numbers, but this is just an intuitive argument, and I don't want to say some rigorous comparison with these two sets. Just a feeling, I think. When you are just a beginner of analytic number theory, I usually recommend you the Apostle's book. Apostle, Introduction to Analytic Number Theory. Which is published by Springer in 1976. This is quite readable book, and any student which I think who can have interest in this prime number theorems or some arithmetical functions or etc. prime zeta function etc. You can enjoy this book quite easily. So this is usually I suggest this as a first reading of the analytic number theory. Maybe if you are more advanced, then probably now the standard reference is so the probably Montgomery and Bohm, or multiplicative number theory. Probably this is Cambridge University Press. This is more advanced textbook, which is maybe suitable for the graduate students for the analytic number theory. But if you are brave enough, probably you can attack this book. Probably these two books are standard, I think. Okay. It is not easy to say why the Riemann hypothesis is so difficult. But one reason is that maybe you know the so-called universality property. Universality. So this is a quite astonishing properties of the zeta function. That if you consider some in the complex plane, you find some compact set, maybe K, and let Fs be the any holomorphic, a bit roughly, but any holomorphic non-zero function in K And for any epsilon, you can find some tau for which the zeta function can approximate this any given f, SF, but arbitrarily accurate, accurately. So I mean, so any holomorphic non-zero function can be well approximate. Any holomorphic non-zero function can be approximated by the Riemann zeta function. This means that Riemann zeta function is very how to say, so usually to prove some theorems in the complex function theory, our usual strategy is to find some nice function which can approximate the target function to get something. But in the case of the Riemann zeta function can approximate any function. That means it is very difficult to find a nice function which can approximate the Riemann zeta function suitably. So this is a so-called universality property. And in my opinion, this is one of the reasons why the Riemann hypothesis is so difficult, because the behavior of the Riemann zeta function is so random and complicated.